Hello everyone, and welcome back to me learning Rust from the Rust book. Today we'll start the 6th chapter about enums and pattern matching. Let's start. In this chapter we look at enumerations, also referred as enums. Enums allows you to define a type by enumerating its possible variants. First we'll define and use an enum to show how an enum can encode meaning along with data. Next, we'll explore a particularly useful enum called option, which expresses that a value can be either something or nothing. Then we'll look at how pattern matching in the match expression makes it easier to run different code for different values of an enum. And finally, we'll cover how the if-let constructor is another convenient and concise idiom available to handle enums in your code. Okay, so as we saw in chapter 2, enums have more punch than the enums that we know from C++ and C and other programming languages, since you can add values to the enum itself, not just the value of the enum, but also a type that associated with a specific enum. So let's start. Okay, defining an enum. Let's first open a project, cargo new chapter 6, and then we code into chapter 6 and go here and here. Great. Okay, let's start. Where structures gives you a way of grouping together related fields and data, like a rectangle with its width and height, enums give you a way of saying a value is one of a possible set of values. Yes, as we know. For example, we may want to say that a rectangle is one of a set of possible shapes that also includes circle and a triangle. To do this, Rust allows us to encode these possibilities as an enum. Let's look at the situation we might want to express in code and see why enums are useful and more appropriate than structs in this case. Say we need to work with IP addresses. Currently, two major standards are used for IP addresses, v4 and v6. Because they're the only possibilities for an IP address that our program will come across, we can enumerate all possible variants, which is where enumerations gets its name. Okay, any IP address can be either a version 4 or a version 6 address, but not both at the same time. This property of IP addresses makes the enum data structure appropriate because an enum value can only be one of its variants. Both version 4 and version 6 addresses are still fundamentally IP addresses, so they should be treated as the same type when the code is handling situations that apply to any kind of IP address. We can express this concept in code by defining IP addr kind, enumeration, and listing the possible kinds an IP address can be, v4 and v6. These are the variants of the enum. So, as I see, to define an enum, we just use the keyword enum, and then the name of the enum, then open brackets, and have the names here. Okay, no semicolon at the end. Probably says I'm not using it. Okay, great. So let's see if there is inherent value. Yeah, we see that v4 is 0 and v6 is 1, as enums in C and C++. Okay, IP addr kind is now a custom data type that we can use elsewhere in our code. Let's do this test. Let for the IP address kind v4, yeah, and let 6 have IP probably something different kind as v6. So this, it doesn't like something here, because this is OP. Great. Okay, so this is of type IP address kind, and this is unused. Okay. Yeah. Note that the variants of enums are namespaced under its identifier, and we use a double colon to separate the two. This is useful because now both values IP kind v4 and v6 are of the same type of IP address kind. We can then, for instance, define a function that takes any IP kind, and we can call this function with either variant. Okay, so let's just play around with it. We can take a called route, and I can get an IP kind of type IP address kind. Yeah, that returns nothing, and I can do let's do nothing. Yeah, this is IP, and then I can do here route 4 and route 6. This should work. Oops. Okay, we have here that it's unused. Let's just do something. Let's try to print it. IP kind. IP kind. Doesn't implement display. What if I do this? Still no display. And okay, I'm not gonna try this. So let's do something like this. Of course, I don't need this. And else print IPv6. Can do a switch statement later. This is weird. I cannot apply this. Interesting. Well, okay, let's forget about this. Let's move on. Using enums has more advantages. Thinking more about our IP address type, at the moment we don't have a way to store an actual IP address data. We only know what kind it is. Given that you just learned about structs in chapter 5, you might be tempted to tackle this problem as structs with as listing like this. So I'm having a struct here that stores the IP kind and a string that it is an address. Then I have two addresses, like a home address and loopback address. Okay, I'm not going to copy this because I think they will show us a better way to do it. Okay, here we define a struct IP address that has two fields. A kind field is of type IP address kind, the enum we defined, and an address field of type string. We have two instances of this struct. First is the home, and is the IPv4, and we have the loopback, which is IPv6. However, representing the same concept using just an enum is more concise. Rather than an enum inside a struct, we can put data directly into each enum variant. This new definition of IP address enum says that both v4 and v6 variants will have associated string values. Okay, so this is what I've been waiting for. So now I can say that I have v4 and v6. Well, oops, sorry, my spelling. So now I have v4, which has a value associated, a string value associated with v4 and a string value associated with v6. I wonder if this still equals 1 or the value replaces the numeric value that usually an enum has. Hence the enumeration thing. Okay, so let's see. So now let's define here. Let home equals IP address kind. Okay. This is not kind anymore. It says IP address v4. It has a string from here, and let loop back equals IP address v6 and have a string from one. Okay, now I'm expecting, okay, there's a problem here. IP address, we have commas, we have everything here. What it says, it's defined multiple times. Sorry, I hate it. I don't like this auto-completion thing. Okay, so now everything looks okay, and let's continue. We attach data to each variant of the enum directly, so there is no need for an extra struct. Here it is also easier to see another detail of how enums work. The name of each enum variant that we define also becomes a function that constructs an instance of the enum. That is, the IP address v4 is a function call that takes a string argument and returns an instance of the IP address type. We automatically get this constructor function defined as a result of defining the enum. Okay, so whenever we use this, there's a function, a method that is created that generates these types of enum structures. Okay, there is another advantage of using an enum rather than a struct. Each variant can have different types and amounts of associated data. Version 4 IP address will always have 4 numeric components that will have values between 0 and 255. If we wanted to store v4 address as 4 U8s, we can do it and still express the v6 as a string. Let's see how they do it. Okay, it's like a tuple here. So we have this, and I guess the constructor will now, oops, need commas, not dots. I guess this works. Yep. So now we have the v4 has 4 bytes associated with it, and the v6 has a string associated with it. Okay. We've shown several different ways to define data structures to store version 4 and version 6 IP addresses. However, as it turns out, wanting to store IP addresses and encode which kind they are is so common that standard library has definition we can use. Yeah, this is the include we had before. Let's look at how the standard library defines IP address. It has the exact enum and variance that we defined and used it, but it embeds the address data inside the variance in the form of 2 different structs, which are defined differently for each variant. So we have this and this. Let's just see if... Okay, they don't tell me where it was. But yeah, but we have 2 different structs that define the parameters in each address kind, and then it defined it like this, nothing different than what we saw here. This code illustrates that you can put any kind of data inside an enum variant, string, numeric types, or structs. For example, you can even include another enum. Also, standard library types are often not much more complicated than what you might come up with. Note that even though the standard library contains a definition for IP address, we can still create and use our own definition without conflict because we haven't brought the standard library definition into scope. What happened to us a couple of minutes ago. We'll talk more about bringing types into scope in chapter 7. Let's look at another example of an enum in listing 6.2. This one has a wide variety of types. So we have an enum message, we have a quit without a type. So let's just copy it. And I want to see what defaults we have here. Yeah, so quit probably without a type equals 0. No, nothing doesn't equal. Move has an. Oh, okay, that's new. Okay, so let's read on and see what it means. So we have an enum has 4 variants with different types. It's a struct. Okay, I defined the struct inline, but I have no keyword struct here. That's interesting. Let's see if I hover. Nothing. Okay, so quit has no data associated with it at all. Move has named fields like a struct does. Write includes a single string, and change color includes 3 I32s. Defining an enum with variants such as ones in listing 6.2 is similar to defining different kinds of struct definition, except the enum doesn't use the struct keyword and all the variants are grouped together under the message type. The following structs could hold the same data that the preceding enum variants hold. So we have a quit message, move message, write message, and the change color message. Okay, so like I'm not sure how this works memory-wise. Like if I'm doing a size of message, am I getting like the biggest size here? And if I want to pack different messages together, are like what is the size and what is the packing? What is the alignment of the data? I'm missing this in this explanation. Let's see if there's like something called size of. Maybe there is. Let size equals size of message. Oh, okay, it's a function. Let's see. Is there a size of here? I don't know. Okay, I guess I'll never know, or maybe later. But yeah, if I do this, then every object has a different size. Like maybe this has size of 12 bytes, this has it's a heap, so probably like, I don't know, 10 bytes. This is 8 bytes, and this is, I don't know, maybe 4 bytes, probably. Okay, but if we use different structs, each of which has its own type, we couldn't as easily define a function to take any of these kinds of messages as we could with the message enum defined in listing 6.2, which is a single type. There is one more similarity between enums and structs, that is just as we're able to define methods and structs using implement, we can also able to define methods on enum. Here the method name call, that we could define our message enum. Okay, so I can define something like this, and I can define the implement message and have a function named call that gets self and does something. Okay, and then I can call, right? I can do here, let's delete the IP thing. I can do let m equals message, I don't know, quit, then I can do m call. Okay, this looks like polymorphism. I guess we need to see how it works out in runtime, or how it affects memory and packing, because I do want to know if I'm defining this type of message and then I'm doing an array of this message or a vector of this message. I want to know like what's the memory structure, what's the memory footprint is going to be. If like there's a certain stride between each of the messages, or you have to jump, I have to like know the type of the enum to jump forward, or it's something like a linked list. I don't know, like we need to see how the memory of this is, how this is represented in memory. Maybe there'll be some kind of paragraph later. The body of the method would use self to get the value that we called the method on. In this example, we've created a variable m that has the value of write message, and that is what self will be in the body of the call method when call runs. Let's look at another enum in the standard library that is very common and useful, option. This section explores a case study of option, which is another enum defined by standard library. The option type encodes the very common scenario in which a value could be something or it could be nothing, like a nullable probably. For example, if you request the first item in a non-empty list, you would get a value. If you request the first item in an empty list, you would get nothing. Expressing this concept in terms of the type system means that compiler can check whenever you've handled all the cases you should. By handling this functionality can prevent bugs that are extremely common in other programming languages. Yeah, they're correct. If you have a way of ensuring that you check for empty lists for some edge cases that are not that are sometimes overlooked, it's good. And if you have actually a way to do this safely while programming, this is really good. So let's see how option is used. Okay. Programming language design is often thought of in terms of which features you include, but the features you exclude are important too. Rust doesn't have a null feature that many other languages have. Null is a value that means there are no value here. In languages with null, variables can always be in one of the two states, null or not null. This isn't correct. In C, C++, no, if you have an int, it cannot be a null. Maybe in some like Python or JavaScript, it can be, but these are not strongly typed languages. Okay, so null basically in C, C++ is defined like null pointer is defined as a pointer type. In C it's a number because there is no null by itself. It's a convention to use 0 as a null pointer, and it's a memory that you cannot work with either way, so that works out. Okay, in this 2009 presentation, null references the $1 billion mistake. Tony Hoare, the inventor of null, has this to say: I call it my $1 billion mistake. At that time, I was designing the first comprehensive type system for references in an object-oriented language. My goal was to ensure that all use of references should be absolutely safe, with checking performed automatically by the compiler. But I couldn't resist the temptation to put in a null reference, simply because it was so easy to implement. This has led to innumerable errors, vulnerabilities, and system crashes, which have probably caused $1 billion of pain and damage in the last 40 years. I have no idea if he's right or not. Yeah, but null checks work, and they help you to avoid this. Null asserts and checks. Okay, the problem with null values is that if you try to use a null value as a not null value, you'll get an error of some kind. Because this null or not null property is pervasive, it's extremely easy to make this kind of error. However, the concept that null is trying to express is still a useful one. A null is a value that is currently invalid or absent for some reason. Yes, this is the reason that you actually start with null. If you want to initialize something, if you want to invalidate some pointer, you put it to null. That way you can check for null and then know that your pointer is invalidated or that the data is no longer valid. The problem isn't really with the concept, but with the particular implementation. As such, Rust does not have nulls, but it does have an enum that can encode the concept of a value being present or absent. This enum is option with an argument, and it is defined by the standard library as follows. So we have a none and we have some t. So t is probably the type that's associated. The option enum is so useful that it's even included in the prelude. You don't need to bring it into scope explicitly. Its variants are also included in the prelude. You can use some and none directly without the option prefix. The option enum is still just a regular enum, and some t and none are still variants of type option t. The t syntax is a feature of Rust we haven't talked about. It's a generic type parameter, and we'll cover generics in more detail in chapter 10. For now, all you need to know is that t means that the some variant of the option enum can hold one piece of data of any type, and that each concrete type that gets used in place of t makes the overall option t type a different type. Here are some examples of using option values to hold number types and string types. So we have some 5, some E, and a none. Okay, so let's just check this out. I want to see that it becomes something here. Oops. It becomes an option I32, and if I put, I don't know, string reference, a slice here, then it will become an option of a slice. And if I do a none, let's see what's the type here. Option unknown. Okay, so the compiler doesn't know what the type is, and it's irrelevant, because if I call sum, probably sum s, it will return, let's see, will this work? Consider giving s an explicit type. Okay, there is no type here, so I have to say what the type is. And let's see, okay, here they're giving it type. Okay, so now if I do option, I don't know, I32, this will work. And this will, let's just print it. I want to see this error. It should be an error, right? Like I'm not mistaken. It's option 32. So we do this. It's still an option, but I want to do something. We have the expect thing. Yeah, we have expect. So here, failed to get num. And then this is. So right now, I'm expecting to get failed to get num. Here it compiles, and when I run, it says failed to get num. And if I put a value here, which is option 5, then I should get 5 printed out. Sorry, sum, not an option, sum. I should get 5 printed out. Okay, great. So we have here the 3 examples with a number, with a character, and with a non-type. The type of some number is option I32. The type of some char is option char, which is a different type. Rust can infer these types because we've specified the value inside the sum variant. For absent number, Rust requires us to annotate the overall option type. The compiler can't infer the type that the corresponding sum variant will hold by looking only at the none value. Here we tell Rust that we mean for absent value to be of option I32. Yes. When we have a sum value, we know that a value is present and the value is held within the sum. When we have a non-value, in some senses, it means that the same thing as null. We don't have a valid value. So why is having option t any better than having a null? In short, because option t and t, where t is any type, are different types. The compiler won't let us use an option t value as if it were definitely a value. For example, this code won't compile because it's trying to add I8 to an option I8. Okay, yeah, this is good. Yeah, because if you had a null pointer, if you have a variable of I8, which is a null, which can't happen in C++, but can happen in Python, JavaScript, TypeScript, etc. Well, maybe TypeScript not. Then you could theoretically add a valid number with an invalid number. So here, because these are different types, the option I8 is different from the I8. It forces you to have a check or to do some sort of value extraction before you can do this summary. So if we run this code, yeah, it yells that there's no implementation for this. Intents. In effect, this error message means that Rust doesn't understand how to add an I8 to an option I8 because they're different types. Yeah. When we have a value of type like I8 in Rust, the compiler will ensure that we always have a valid value. We can proceed confidently without having to check for null before using that value. Only when we have an option I8 or whatever type value we're working with do we have to worry about possibly not having a value. And the compiler will make sure we handle that case before using the value. So it's basically like a gate that protects the value. Yeah, we have to open the gates and see if there is a value or there isn't a value before we can use it. Yeah, that is the way of the compiler to make sure that we're accidentally not using a null value or a non-existing value. In other words, you have to convert an option to a type before you can perform operations on the type. Generally, this helps catch one of the most common issues with null, assuming that something isn't null when it actually is. Eliminating the risk of incorrectly assuming a non-null value helps you to be more confident in your code in order to have value that can possibly be null. You must explicitly opt in by making the type of that value option T, then you use that value. You are required to explicitly handle the case where the value is none. Everywhere that a value has a type that isn't an option, you can safely assume that the value isn't null. This was a deliberate design decision for Rust to limit null's pervasiveness and increase the safety of Rust code. That makes sense. So how do you get the T value out of some variant when you have a value of type option T? So you can use that value. The option T enum has a large number of methods that are useful in a variety of situations. You can check them out in its documentation, and becoming familiar with the methods of option T will be extremely useful in your current journey. Yeah, so now we used expect here, what we saw in chapter 2. I think, yeah, but you have like a lot of functions here. You have even okay, or interesting. Okay. In general, in order to use an option T value, you'll want to have code that will handle each variant. You want some code that will run only when you have some T value, and this code is allowed to use the inner type. You want some other code to run only if you have a non-value, and that code doesn't have a type value available. The match expression is a control flow constant that does just this. When used in enums, it will run different code depending on which variant of the enum it has, and that code can use the data inside the matching value. I think we saw it in chapter 2 with the different like outcomes of the larger. We had some comparison function that returns an enumerator about equality, if it's greater, lesser, or equal, and then we use this. So let's think next chapter we'll have something like this. So, okay, Rust has an extremely powerful control flow construct called match that allows you to compare a value against a series of patterns and then execute code based on which pattern matches. Pattern can be made up of literal values, variable names, wildcards, and many other things. Chapter 18 covers all the different kinds of pattern and what they do. The power of match comes from the expressiveness of the patterns and the fact that the compiler confirms that all possible cases are handled. This is important, yeah. It's also in, like, there's a warning flag you can do in C that checks that whenever you have a switch or a match in this case, that you cover all the options, all the possibilities that could be there. So it's good. Okay. Think of a match expression as being like a coin sorting machine. Coins slide down a track with variously sized holes along it, and each coin falls through the first hole it encounters that it fits into. In the same way, values go through each pattern in a match, and at the first pattern the value fits, the value falls into associated code block to be used during execution. Similar to the switch cases, but switches also continue. If you don't break from the switch, they continue forward. We'll see if this is also the case here. Okay, so speaking of coins, let's use them as an example using match. We can write the function that takes an unknown US coin and in similar way as the counting machine determine which coin it is and return its value in cents as shown in listing 6.3. So we have an enum called coin that has values of penny, nickel, dime, and a quarter. And then we have a function value in cents of a coin, and then it returns a U8, and then we have a match coin, match coin, and here we have coin penny goes to 1. We have here 5, 10, 25. What? Something is weird here. Okay. This is weird copy paste here. Let's go to nickel, a dime, and a quarter. Okay, so this returns, because we don't have a semicolon here, this returns the value. This value is probably U8 because of this. Okay, let's continue. There's no error here. And coin is never used. Okay. Let's break down the match in the value in cents function. First, we'll list the match keyword, followed by an expression, which is, in this case, is the value coin. This seems very similar to a conditional expression with an if, but there's a big difference. With if, the condition needs to evaluate to a Boolean value, but here it can be of any type. The type of the coin in this example is the coin enum that we defined on the first line. Next are the match arms. An arm has two parts, a pattern and some code. The first arm here has a pattern that is the value penny, and the arrow operator that separates the pattern and the coin and the code to run. The code in this case is just the value 1 that will be returned by the function. Each arm is separated from the next with a comma. Okay. When the match expression executes, it compares the resultant value against the pattern of each arm in order. If a pattern matches the value, the code associated with that pattern is executed. If that pattern doesn't match the value, execution continues to the next arm, much as in coin sorting machine. We can have as many arms as we need. In listing 6.3, our match has 4 arms. The code associated with each arm is an expression, and the resultant value of the expression in the matching arm is the value that gets returned for the entire match expression. So basically, I think this example answers the question that I had before, that you don't have to break, that if the coin matches penny, only this will run, because then it has problem of which type to return, basically, if I don't stop it. So each arm is independent, and there is no flow from one arm to another, like a switch statement in C. Okay. We don't typically use curly brackets if the match arm code is short, as it is in listing 6.3, where each arm just returns a value. If you want to run multiple lines of code in match arm, you must use curly brackets, and the comma following the arm is then optional. For example, the following code prints lucky penny every time the method is called with a coin penny, but still returns the last value of the block 1. Okay, so here I don't need the comma, multi-line. Let's just implement this here. I have print line lucky penny, and then 1. Great. Okay, pattern that binds to values. Another useful feature of match arm is that they can bind the parts of the value that match the pattern. This is how we can extract values out of enum variants. In an example, let's change one of our enum variants to hold data inside it. From 1999 through 2008, the United States minted quarters with different designs for each of the 50 states on one side. no other coins got state design, so only quarters have this extra value. We can add this information in our enum by changing the quarter variant to include a US state value stored inside it, which we've done in listing 6.4. So let's just copy this. So I have another enum of US states. Currently, sorry, but we only have 2 states. But we can add a quarter here. So now this has an error. So let's see. So the coin cannot be a quarter anymore. This is weird. What's the error? Okay, probably there's other way we can mark this. So let's continue reading. Okay, let's imagine that the friend is trying to collect all 50 state quarters while we sort out loose change by coin type. We'll also call out the name of the state associated with each quarter, so that if it's one of our friends doesn't have, they can add it to their collection. Okay, so here I have to actually put this like this for the match to put the value inside. Yeah, so now there's a US state, and in addition to printing out the value, of returning the value, I can print, a quarter from, and then put a state here. It doesn't like it. Doesn't implement the display. Okay, I need to do this, the debug thing here. Okay. Great. If we were to call value in cents like this, let's try. Let's just try doing this. There are some warnings, but I get quarter from Alaska. So basically this, the derived debug thing, also tokenizes this enum. That's nice. That's good for the debugging. Okay, if we call this coin, we would get, the coin will be a US quarter with Alaska inside. When we compare that value with each of the match arms, none of them match until we reach the coin quarter. At this point, the binding for state will be the value of Alaska. We can then use that binding in the print line expression, thus getting the inner state value out of the coin enum variant for quarter, matching with option T. In the previous section, we wanted to get the inner T value out of the sum case when using option T. We can also handle option T using match, as we did with the coin enum. Instead of comparing coins, we'll compare the variance of option T, but the way the match expression works remains the same. So we have function. Let's just define a function here with con +1 that gets that when the first argument is an option of type i32, and it returns an option of type i32, and then scroll here, and then once again we have a match of x. Sorry, a match of x. If it's none, then I return none. Right, the function returns none, and if I have sum I, then I return sum I plus 1. So let's go over the code before I read the text. So we have a function that gets an option i32. We'll then run it through a match. If it matches to a none, if there is no value inside this option, we return a none here. A none, as you recall, is of type option. So it is an option i32. And if we have some value, and the value is I, we return an option that, as you recall, we declare as sum with a value I plus 1. Yeah, so I guess we don't need to check this. I could just copy paste it, see that it see that it compiles. Yeah, we have just warnings. Okay, I have a 5 that I declare. I do a +1 on 5, get a 6. And if I do +1 on none, I still get something that's valid. Okay. Okay, so I think we've examined this. I read fast through it. Let's examine the first execution of +1 in more detail. When we call +1 5, the variable x in the body +1 will have the same sum 5. Then we compare that against our match arm. This will not compare, this will compare. We have the value 5 here, and then we'll return the sum with value 6. Does sum 5 match sum I? It does. We have the same variant. The I binds to the value contained in sum, so I takes the value 5. The code in the match arm is then executed, so we add 1 to the value of I and create a new sum value with our total 6 inside. Now let's consider the second call, where x is none. We enter the match and compare the first arm. It matches, so there's no value to add to, so the program stops and returns the none value on the right side of the arm. Because the first arm matched, no other arms are compared. Combining match and enums is useful in many situations. You'll see the pattern in a lot of Rust code. Match against an enum, bind the variable to the data inside, and then execute code based on it. It's a bit tricky at first, but once you get used to it, you'll wish you had it in all languages. It's consistently a user favorite. Matches are exhaustive. There is one aspect of match we need to discuss. The arms pattern must cover all possibilities. Consider the version of our +1 function, which has a bug and won't compile. Okay, this one won't compile because I'm not covering the none, right? Yeah. We didn't handle the none case, so this code will cause a bug. Luckily, it's a bug Rust knows how to catch. If we try to compile the code, we get an error. Okay. Rust knows that we didn't cover every possible case and even knows which pattern we forgot. Matches in Rust are exhaustive. We must exhaust every last possibility in order for the code to be valid, especially in case of option, when the Rust prevents us from forgetting to explicitly handle the none case. It protects us from assuming that we have a value when we might have null, thus making the $1 billion mistake discussed earlier impossible. Okay, catch all patterns and the underscore placeholder. Using enums, we can also take special actions for a few particular values, but not for all other values. Take one default action. Imagine we implementing a game where if you roll a 3 on a dice, your player doesn't move, but instead gets a new fancy hat. If you roll a 7, your player loses the fancy hat. For all other values, your player moves that number of spaces on the game board. Here's a match that implements that logic with the result of the dice roll hard-coded, rather than a random value. And all other logic represented by functions without bodies, because actually implementing them is out of scope for this example. So I'm not copy-paste this. So we have a dice roll and we have a match. If it's 3, then add fancy hat, 7, remove fancy hat, and all other, so other is the keyword here, move player. And we have these kind of functions. So basically the other covers everything else in the match. For the first two arms, the patterns are literally values 3 and 7. For the last arm that covers every other possible value, the pattern is the variable we've chosen to name other. The code that runs for the other arms uses the variable by passing it to the move player function. Okay, so if I don't have to put an other here, I can put anything I want, and this becomes the variable of this arm, and I can use this inside this arm. Okay, the code compiles even though we haven't listed all possible values a U8 can have, because the last pattern will match all values not specifically listed. This catch-all pattern meets the requirement that match must be exhaustive. Note that we have to put the catch-all arm last because the patterns are evaluated in order. If we put the catch-all arm earlier, the other arms would have never rust. So rust warns us, and if we add arms after catch-all. Okay, so this is a warning, it's not an error. We can use this in debug times when we want to eliminate some choices really quickly. Instead of commenting them out, we can move them. Yeah, nice. Rust also has a pattern we can use when we want to catch all but don't want to use the value in the catch all pattern. An underscore is a special pattern that matches any value and does not bind to that value. This tells Rust we aren't going to use the value, so Rust won't warn us about an unused variable. I think we saw that it's not only in match values. When you use an underscore, it's something, it indicates to the compiler that it's a value you just want to throw out. Let's change the rules of the game now. If you roll anything other than a 3 or a 7, you must roll again. We no longer need to use the catch-all value, so we can change our code to the underscore instead of the variable named other. Okay. This example also meets the exhaustiveness requirement because we're explicitly ignoring all other values in the last arm. We haven't forgotten anything. Finally, we'll change the rules of the game one more time so that nothing else happens on your turn if you roll anything other than 3 and 7. We can express that by using the unit value, the empty tuple type we mentioned in the tuple types section. I think it was chapter 3. As the code that goes with the underscore arm. Okay, so here, basically we say nothing happens. Just if you do this, nothing happens. Okay, here we're telling Rust explicitly that we aren't going to use any other value that doesn't match a pattern in an earlier arm. If we don't want to run any code in this case. There's more about patterns and matching that we'll cover in chapter 18. For now, we're going to move on to the if-let syntax, which can be useful in situations where the match expression is a bit wordy. Okay, let's delete things here. Okay, so the if-let syntax lets you combine if and let into less verbose way to handle values that match one pattern while ignoring the rest. Consider the program in listing 6.6 that matches on an option U8 value in the config max variable, but only wants to execute code if the value is the sum variant. So we have here variable, some variable that has some value, 3 of U8, and we're matching this, and if there is some, we're printing it, and if it has no value, we do nothing. If the value is sum, we print out the value in the sum variant by binding the value to the variable max in a pattern. We don't want to do anything with the non-value to satisfy the match expression. We have to add this after processing just one variant, which is annoyingly boilerplate code to add. Instead, we could write this in a shorter way using if-let. The following code behaves the same as match in listing 6.6. Okay, so here we have if, and then let sum max equals config max, and then we print max. So basically, yeah, it's the pattern matching thing, right? Because we have this pattern which defines a variable sum with the max type, and then I'm assigning the config max to this type, and then I'm printing. And the if, I don't know if only works when there's an option. Maybe it's written here, but what we're getting is the assignment of the value of config max into the max. Okay, the syntax if-let takes a pattern and an expression separated by an equal sign. It works the same way as match, where the expression is given to the match and the pattern is its first arm. In the case, the pattern is sum max, and the max binds to the value inside sum. We can then use max in the body of the if-let block, and in the same way we used max in the corresponding match arm. The code is in the if-let block isn't run if the value doesn't match the pattern. So basically it's, okay, so it's not evaluated as a Boolean here or something, it's evaluated as an arm. Like if the config max matches this pattern of sum max. Okay, so it's just like an arm of the switch state. Okay, using if let means less typing, less indentation, and less boilerplate code. However, you lose the exhaustive checking that match enforces. Choosing between match and if let depends on what you're doing in your particular situation, and whether gaining consciousness is an appropriate trade-off for losing exhaustive checking. In other words, you can think of if let as syntax sugar for a match that runs code when the value matches one pattern and then ignores all other values. We can include an else with an if let. The block of the code that goes with the else is the same as the block of code that would go with the underscore case in the match expression that is equivalent to the if, let, and else. Recall the call enum definition in listing 6.4, where the quarter variant also held the US state value. If you wanted to count all non-quarter coins we see while also announcing the state of quarters, we could do this with a match expression like this. So we have, like, if we find the quarter, we print its state, and if we don't, and for anything else, we just increment this this variable. Or we can use a let if that basically matches against this, and if it matches, then it prints, and else is just increments. This is one line more. Okay, summary. We're now covered how to use enums to create custom types that can be one of a set of enumerated values. We've shown how the standard libraries option type helps you use the type system to prevent errors. When enum values have data inside them, you can use match or if let to extract the use and use those values. Depending on how many cases you need to handle, your Rust program can now express concept in your domain using structs and enums. Creating custom types to use with your API ensures type safety. The compiler will make certain your functions only get values for the type each function expects in order to provide a well-organized API to your users that is straightforward to use and only exposes exactly what your users will need. Let's now turn into Rust modules. Okay. So yeah, they're right. Basically, the tools we've seen so far will help me, when writing code, design such an interface, such an API that will prevent people who are using my code, or even myself, from making small mistakes by being unattentive to null values, by allocations and definitions, by being very strict with type, and by forcing me to explicitly say when something can be null, and also explicitly handle the cases where it is null. Okay, so next chapter is probably about modules. We'll do it next time. Thank you very much. Goodbye.